So these overlapping sub-problems actually cause a lot of waste, because we have to calculate the same sub-problems over and over again, and thus so much computational time and resource is lost. So how can we get around this problem? Well, let's think about it like this. If the first time when we calculated one term, let's say f6, we know the value of it, right? What if we didn't need to calculate it for a second time, or however many times we will need it further on? If we store the value of f6 somewhere, as I stored someone's name in my memory, it's like a phone book. When you first take a number from someone, you ask for it and then you save it in your phone book, right? And further on, whenever you want to call that person, you don't have to type the whole number again. You just go to his or her contact and call him or her from there, right? We're going to do something of the similar fashion. We're going to store a value, and then when someone asks for it, we will just tell them the value from memory. Only the first time we will calculate the value, and for all the other times we will just say it from memory. So how can we do that? Let's see that. So let's take a little smaller example. Let's say f6, and then we want to calculate f5. It calls for f4, it calls for f3, and it calls for f2. It calls for f1, gets the value, then it calls for f0, and then f2 is calculated, it will be 1. So what we're going to do, we're going to use a storage. A storage like what? A storage like a simple array. Let's think about it like an array. Oh, sorry for the curved line. Okay, so let's say this is an array, and these are the index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's initially we keep all the values as -1. We'll explain it later why we're keeping -1, but for now let's just say we're keeping it -1. And there's no reason I built the letter till 9. It's actually continued. You can continue it however long you want. I'm just giving an example. So let's say this will be the modified array. I am not deleting the previous array. Let's say I will just modify it. So these will represent the present values of the array. Initially all are -1. So f1 and f0, these are pre-declared, right? So these two will not be -1. So these two will be, let's say, 0 and 1. Let's say I change my color here. All right. Okay. Apparently it's not letting me change the color. Okay, let's continue. So when f2 is calculated, f3 will actually call for f1, and this will get 1, and it will be calculated as 2, and f4 will call for f2. Now as you see, f2 is already calculated, but we have to calculate it once again, but we want to avoid that, right? So how we can avoid that? See, when you calculated f2, you got the value 1. So what if we wrote this value into the array and stored it there, and the next time someone asks for f2, let's say here f4 is asking for f2, it actually checks on the array and it sees that its value is already calculated, it's 1, and it just returns from there that the value of f2 is 1. It doesn't have to calculate by summing up f1 and f0. It just returns the value from here. And now f4 is calculated as 3. Similarly, when we have calculated f3, we can actually store it in this array, overwriting the previous value. And now when we have calculated f4, we can actually store it in the array. And what will happen now? f5 will ask for f3 as it has completed calculating the value of f4, and as we can see, the value of f3 is already stored in the array. We don't need to calculate it once again. That means this portion here is not needed to be calculated anymore. It can actually return this value from the array to f5, and f5 can be calculated now as 5, and so we write it here. And then when f6 asks for f4, it doesn't have to look below again to calculate this portion. It can actually return directly from this array, and as it returned f5 is 5 and f4 is 3, f6 will be 8. And that's actually the way of avoiding the calculation of one value multiple times by storing it in some storage, in this case an array, and that's the way of working around it. So now we will actually see that why these minus ones are needed, because we initiated the whole array with minus array. Now we'll see what these minus ones are for, because we initialized the whole array with minus 1. And why is that? We could have left it blank, or maybe some random values. That could be the thing also. Now we will see that what these minus ones are for. We initially initialized the whole array with minus ones, but why is that? What if there were some random values in the array initially? Will that cause a problem? Well, in this case, yes, but what is the problem? We'll see to it. So let's go for a fresh example. Let's say here we have our array. Okay, these are the indexes and initialized with minus 1. And let's say we'll modify the array here. So when we start or want to start calculate f5, we ask for f4. Now you see, how do you know that f4 has been calculated or not? That's why we use minus 1. If the fourth index of the array is minus 1, that means that f4 has not yet been calculated. It will be calculated. And when we ask f3, we see that f3 has not been calculated. So we go on further to f2. And f2 also has not been calculated. So we go on further for f1 and f0. Now if I want to modify the color, f1 and f0, these will be initially predetermined by 0 and 1. These will not be minus 1, because otherwise it will go on forever. So f1 will return 1 and f0 will return 0, and f2 will be calculated as 2. And when it is calculated as 2, we will override this minus 1 and replace it with 2. Well, actually I did a very silly mistake there. It will be 1. Obviously 0 and 1 sums up to 1. Yeah, so it will be 1, and I write the value here as 1. Now F3, it will ask actually that what is F1, and it will return 1, and so this value will be calculated as 2, and we will write 2 here. Now what is the purpose it serves? You see that F4 will ask for F2, and now if we check in the array, we'll see that the second index of this array doesn't contain -1 anymore, it now contains 1, and so it will realize that F2 has already been calculated, and it won't go further down to calculate it from F1 and F0. It will actually return F1 directly, and F4 will be calculated as 3, and we will write it here in this array. So -1 is for the checking of a value that it has been calculated already or not. So now you may ask a question that why -1? Why nothing else? Why not 100? Why not 10 or -5? Well, the main reason behind it is that you have to initialize the array with something invalid, because if you initialize it with, let's say, 5, it may not work, because 5 is a valid Fibonacci number. So if we initialize the whole array with 5, then this value here will not be -1, it would be 5, and when we check this is 5, we will just return 5 from here, but that may be wrong, although in this case this is right. But if we initialize the whole array with 5, then this value here would be 5 also, but that is not correct. This should be actually 8 when calculated. But when we see 5, how would we know that this is not a valid Fibonacci number? It may be a valid Fibonacci number, it may not be a valid Fibonacci number. So we can't put anything positive in those arrays initially, because positive numbers may be a possible Fibonacci number. But if we put any negative number here, let's say we initialize the array, the whole array with -10, that will actually work, because no Fibonacci number can be -10. So if we see -10 in any of these indexes, we will be sure that this value has not been already calculated. We have to calculate it. And if we see anything other than -10, then we will be sure that this value has already been calculated, because you see, at first the 5th index or the 4th index or any of the indexes will contain -10, and when it will be calculated, it will replace the value with something like, let's say, 5 or 8, or it could be 13, anything, and it will not be -10. So we will realize that this has already been calculated. So -1 is just an invalid number. We can use it. If you want, you can use -10, -100, -53, but not any positive number. You have to use something invalid that cannot be the value of a Fibonacci number. And now you may say that, okay, 23 is not the value of a Fibonacci number. Can we use 23? Yes, we can, but that actually requires you to know from beforehand that 23 is none of the Fibonacci numbers, right? But negative numbers can never be a Fibonacci numbers. So you just have to have that knowledge that Fibonacci numbers can't be negative. That's why you can use any negative number, and that's more user friendly, or you should say easier. So how should we code this thing? How to code this new thing that will avoid overlapping subproblems? Because the previous code we had, that is this, actually contained this problem. It didn't store the values anywhere. So now let's see. Okay, so I have actually written on this sheet, so I will just delete it just to see. Okay, so we can actually see that there will be an array. Let's say we will define an array that is called f, and the nth index of this array will contain the nth Fibonacci number. This fn will contain the nth Fibonacci number. So when we are trying to calculate fib of n, and this is calling fib of n minus 2 and n minus 1 and adding them, we are storing this value in this array, and then we will return this value. So you see what happens here. Whenever f3 or f2 is calculated, it is getting stored in the array that we used. And later on, whenever someone asks for f3, it will actually check in this array and return this value because it's already determined. So how will we check this? This is the base case as always, and then before going to this phase, because we are calculating f of n here, and we have to check before calculating that if it's already calculated. So we will insert a line here that if fn is not equal to -1, you look at this carefully, not equal to, because if f of n is equal to -1, that means that this has not been calculated, it has to be calculated, so we will calculate it. But if it's not -1, that means it's something else, which means that fn has already been calculated, so we will just return this value from here. And that's how this will avoid the overlapping subproblems, because let's say f3, the first time when we are going to check f3, we will see that it is -1, so this condition will not hold. It will continue to this line and it will calculate f3, store it and return. But the next time we are asking f3 to be calculated, it will see that this time the array doesn't hold -1, it holds the value 2, and that's why this condition will be fulfilled, at this f of n will be returned from here. And now to give you a little idea that how much this being stored helps, we will look at something. Let's say you want to calculate Fibonacci of 100, that is the 100th element of this series. So you will ask for the 99th element and also needs the 98th element, and this 99th element needs the 98th element and the 97th element, and this 98th element will be actually calculated, and this will be a pretty huge portion, you can imagine. Now if we didn't use the storage technique, that we are storing the values, this huge portion, this would also be calculated here. And don't think this is a small portion, this is quite a huge portion. If you simulate it, you will realize how large it is. And now by storing, we can totally avoid this being calculated a second time. Also many other portions would be calculated multiple times, but now they will be calculated only one time, and after being calculated only one time, they will be stored in the array, and later on we don't have to calculate anymore, we can return it from the storage. So that's how this technique, this storing technique, reduces the complexity, or you could say that the wastage of resources or time from this algorithm. So now we would like to see that what this technique is called. So this storage technique, or we should say that we are storing the values in an array, right? What is this called? So this technique is actually called memoizing or memoization. Yes, you have seen it right, you have heard it right. This is memoization, not memorization. And you may ask, has your whole life been a lie? No, it has not been, because memorization is also a term. Typically we use memorization when we actually memorize something. Let's say you actually memorize the first 1000 Fibonacci terms, and whenever someone asks one of them, you just blurt it out from your memory. That's called memorization. But in this technique, in this portion, what we didn't memorize it at first. For any value, let's say the 57th value of the Fibonacci number, we actually calculated it the first time, and then we stored it in memory. And when the next time someone asked what is the 57th or the 67th or the 73rd element was, at first, if we don't know it, we calculate it, and after calculating it once, we say it from memory. That's why this is called memoization, not actually memorization, but close to it. That's why memoization. So we're right now to the end of this video, and we would like to point out actually two major things that we discussed, that is overlapping subproblems and memoization. These two are very important properties of dynamic programming. That's why I discussed it at first with a simple problem. There is also a third portion which is called optimal substructure, which we will discuss on the next video, and these three actually makes dynamic programming as a whole. These are the three important components that makes dynamic programming a nice and beautiful technique.